We often think that setting foot on the moon is the hardest part of the journey, but for astronauts, the real challenge lies in returning safely to Earth, because reaching that destination does not mean you have escaped danger. In space, everything operates under absolute physics, and even the smallest margin of error in speed or trajectory can cause a spacecraft to never find its way back. Unlike on Earth, you cannot stop or turn around when you go off course, because out there is no such thing as a stopping point or a second chance to correct a mistake in the usual way. To return, a spacecraft must achieve near-perfect precision in speed, timing, and re-entry angle. If it is slower than required, it may not have enough energy to escape the moon's gravity. But if it is too fast or slightly off course, and it can slip out of trajectory and vanish into deep space. What sounds like a simple round trip is in reality more like launching an object into the unknown and forcing it to return to the exact point of origin while both are in motion. Every phase of the journey is a one-time opportunity where no mistakes are allowed. Once you leave Earth, there is no way to stop, fix an error, or wait to be rescued. Everything required for survival, from fuel, oxygen, and energy to drinking water, must be prepared from the moment of departure. And most importantly, it must be enough to ensure that the mission is not only possible, but that a return is guaranteed. What makes this journey truly terrifying is this: the return does not begin when leaving the moon. It is determined from the very moment the spacecraft departs from Earth. But if the mass is miscalculated, the fuel is misjudged, or the initial trajectory is not set precisely, the crew may still reach the moon, but they will never have a chance to come back. So the question is not only how to get there, but how to leave and return to the exact place of origin. Earth does not stand still waiting for them. It is constantly rotating and moving through space, forcing the spacecraft to calculate a precise rendezvous with the planet from an immense distance. That is why missions like Apollo 11 succeeded not only because of the power of the rocket, but because of the near-perfect accuracy in every orbital and timing calculation. If the journey outward is a battle against gravity, then the journey back is a battle against a margin of error, speed, temperature, and time. In particular, at the re-entry phase is one of the most dangerous moments, where even the slightest deviation in angle can cause the spacecraft to burn up or skip back into space. In other words, from liftoff to a safe landing in the ocean, the entire mission is a chain of precise calculations where human lives depend entirely on numbers. And that is what makes the story of the moon so extraordinary, because humanity was not only brave enough to leave Earth, but knowledgeable enough to find the way back. Up to this point, we have only touched on the first question, and to understand how humans truly managed to achieve it, everything must begin from the moment of departure from Earth. Every mission to the moon starts with a challenge that may seem simple, yet is one of the greatest barriers: escaping the gravity of the planet we live on. And Earth is not just our home, it is also a massive gravitational field that holds everything in place, and to break free from it, a spacecraft must reach an escape velocity of about 6.95 miles per second, equivalent to over 24,855 miles per hour, an extremely demanding figure in real-world engineering. If it fails to reach this threshold, it will be pulled back down. But if it succeeds, only then can it begin its journey away from the planet, little by little. The problem is that reaching such speed requires an enormous amount of energy, which is why most of a rocket's mass is not people or equipment, but fuel. In systems like Saturn V, more than 85% of the launch mass is fuel, used solely to overcome Earth's initial gravitational pull. To optimize this, engineers developed multi-stage rocket designs, where each stage separates after its fuel is depleted, reducing mass and allowing the remaining sections to accelerate more efficiently. Thanks to this mechanism, the rocket does not carry dead weight throughout the journey, but continuously sheds what is no longer needed, step by step pushing the spacecraft closer to deep space. Even after leaving the launch pad, the spacecraft has not truly escaped Earth. It is still being constantly pulled back by gravity and must continue accelerating to reach escape velocity, the threshold at which it no longer falls back. Only when it reaches about 6.95 miles per second does it officially break free from the planet's direct grip, but that does not mean it flies straight toward the Moon. Instead, it is placed into a curved orbit around Earth, and calculated with extreme precision down to the smallest detail. From this orbit, missions like Apollo 11 perform a critical maneuver known as translunar injection, a precisely timed engine burn that pushes the spacecraft out of Earth's orbit and sets it on a path toward the Moon. But if this departure phase from Earth is even slightly off, the entire journey that follows becomes almost impossible to recover because in space, there is no concept of turning back to start over. Everything is predetermined by calculations made before launch, and any error will only grow over time. That is why the launch is not simply a beginning. It is the foundation that determines whether the spacecraft can complete both the journey out and the return home. And once it escapes Earth's primary gravitational pull, as the spacecraft enters an entirely different phase, where there is no clear road ahead, only trajectory and mathematics guiding the way. Once it leaves the region of Earth's strongest gravitational influence, the spacecraft does not travel along any predefined path, but instead moves into a completely empty environment, where there are no landmarks, no signals, and no indicators to tell whether it is on course or off track. Unlike the way we navigate on Earth, the journey to the Moon is not guided by intuition, but by an orbital problem defined by physics and time. The spacecraft does not fly straight toward its destination, but is placed into a curved trajectory where every movement is governed by gravity. In reality, it is in a constant state of falling, but falling with enough precision to avoid colliding with any celestial body. This is the fundamental principle of all spaceflight. To reach a destination, you sometimes do not move directly toward it, but instead follow a path that has been calculated in advance. Even the smallest deviation in speed or trajectory can cause the spacecraft to drift hundreds, even thousands of miles off course as the distance stretches into hundreds of thousands of miles. That is why missions like Apollo 11 rely entirely on extremely precise guidance systems, continuously determining the spacecraft's position and direction in space. However, even with computer assistance, every engine burn must be calculated with near-perfect accuracy, because there are moments when the engine fires for only a few seconds, and even a slight underburn or overburn can send the entire mission off its intended path. The movement in space is not a continuous acceleration, but for most of the journey, the spacecraft simply drifts along a trajectory that has already been calculated in advance, almost in complete silence. On the surface, everything may appear stable, but in reality, every aspect depends on the calculations running behind the scenes, determining whether the spacecraft still has a chance to return. Each trajectory correction is a very small adjustment, yet it carries life or death significance, because in this environment, intuition has no value, and every decision must rely entirely on mathematics and data. That is why missions like Apollo 11 are prepared over many years, because there is no room for improvisation. As the spacecraft approaches the Moon, the complexity increases significantly, because it begins to feel the influence of another gravitational source, forcing the entire trajectory to be recalculated. From this point on, the objective is no longer just to approach, but to ensure that the spacecraft is actually captured by the Moon. If this step is not executed correctly, the spacecraft will simply pass by and continue drifting into deep space. Unlike Earth, the Moon has no atmosphere to assist with deceleration, so the entire braking process must rely on the engines. At the moment of approach, the spacecraft is still carrying a very high velocity from the earlier phase of the journey, and to enter orbit, it must slow down at exactly the right time and by the right amount. If it slows too little, it will fly past, but if it slows too much, it can disrupt the entire trajectory. As this is one of the most delicate phases of the mission, where the spacecraft must slip deep enough into the Moon's gravitational field to be captured, while still maintaining control of its motion instead of falling straight to the surface. This phase is known as lunar orbit insertion, a mandatory step before any attempt can be made to land on the surface. In essence, the spacecraft must transition from flying through space to being captured and beginning to orbit the Moon. To achieve this, every factor, speed, approach direction, and engine ignition timing, must be synchronized with near-perfect precision. Even a delay of just a few seconds in an engine burn can completely alter the resulting orbit, and in space, such a small error can quickly expand into tens or even hundreds of miles. For that reason, astronauts cannot rely on instinct, but must place complete trust in guidance systems, sensors, and pre-calculated plans. As the spacecraft draws closer to the Moon, judging distance and speed becomes increasingly difficult due to the absence of an atmosphere or any familiar reference points like those on Earth, leaving only silence and the cold gray landscape stretching below. That is why the approach phase is not a moment of rest, but one of the most dangerous periods of the entire mission. If executed correctly, the spacecraft will be held in a stable orbit, ready for the landing phase. But if it fails, the entire journey can end right there. After traveling nearly 248,548 miles, even a single small mistake is enough to turn that entire distance into a journey with no chance of return. Even after stabilizing in orbit, the most difficult part of the mission still lies ahead, landing on an environment that allows almost no margin for error. Although the distance from orbit to the surface is small compared to the entire journey, this is the most dangerous phase. From above, the Moon's surface may appear calm and within reach, but to touch down safely, the spacecraft must go through a sequence of extremely precise operations. Unlike on Earth, where the atmosphere naturally helps slow things down, the Moon has virtually no atmosphere, meaning the entire deceleration process must rely completely on the engines. If this system does not function correctly, the spacecraft will descend at high speed with no way to stop. For that reason, landing on the moon is not a touchdown in the usual sense, but more like holding the entire spacecraft suspended by engine thrust while gradually reducing altitude. Throughout this process, the spacecraft must slow down, control its descent path, and at the same time identify a sufficiently safe landing area, where every decision must be made with near-perfect precision. In reality, the surface of the moon is far from flat as many might imagine, but instead a landscape filled with craters, large rocks, steep slopes, and a fine layer of dust covering everything. Landing at even a slightly unstable angle can cause the spacecraft to tip over, and striking an obstacle in the wrong place can bring the entire mission to an immediate end. As the spacecraft nears the ground, another problem emerges. The exhaust from the engines blasts the fine dust into the air, creating a thick cloud that completely obscures visibility. In the final seconds, when every margin of error becomes most dangerous, the astronauts can barely see the surface below. For that reason, the landing cannot rely on instinct but must depend on radar, measuring altitude, velocity, and data from control systems. However, even when the instruments function perfectly, humans must still make decisions within extremely short time frames, continue the landing, or abort to avoid risk. During the Apollo 11 mission, the astronauts were forced to adjust the landing site at the last moment when the original area proved unsafe, while the remaining fuel was only enough for a few dozen seconds. That meant that at the very moment they were about to touch another world, they were also closer to failure than ever before. A landing is only considered successful when the spacecraft touches down gently, remains stable, and maintains balance. When the engines shut down and the spacecraft stands still, it is not just a landing, but the result of countless calculations executed with precision. And only from that moment can humans truly set foot on the surface of the moon, and rather than simply passing by it in space. But the paradox of this journey lies in the fact that a safe landing has never meant they were out of danger. The very moment they touched down on the moon, the vehicle that brought them there instantly became the only hope for leaving and returning to Earth. So after that historic landing, the next major concern emerged almost immediately: how to lift off again from a world that allows no room for error. Many assume the hardest part ended when humans set foot on the moon, but in reality, another life-critical challenge had just begun, because they could not stay. They had to return using the very small spacecraft standing on the surface. Unlike the launch from Earth with a massive rocket and an entire ground control network, this departure from the moon depended entirely on the ascent stage engine of the lunar module, the same place where the astronauts had lived and worked during their time there. If that system failed to ignite at the right moment, there would be no rescue option, no realistic backup plan, and no other way to leave the moon. That is why, before liftoff, every piece of equipment had to be checked with the highest level of rigor, because once the ignition command was given, the fate of the entire crew rested entirely on the reliability of a single machine. At the moment of departure, the upper section of the lunar module separates, leaving the entire landing stage behind on the surface of the moon, and it marks the only time in human history that a launch has taken place from another celestial body using such a small vehicle. There is no air, and no sound, only the thrust of the engine lifting the spacecraft away from the cold gray surface. The spacecraft accelerates not to completely escape the Moon, but to return to a pre-calculated orbit. There, a critical task awaits: docking with the command module still orbiting the Moon, as in Apollo 11. That means a successful liftoff is not enough. They must also locate and reconnect with their mothership, which is constantly moving through space. This is not a case of two vehicles traveling along the same path, but two objects flying on separate trajectories that must meet with near-perfect precision. Even the smallest deviation in speed or approach angle can cause them to miss each other and lose any chance of reconnecting. For that reason, the process is carried out extremely slowly, step by step, and under the strict control of both the astronauts and onboard computer systems. When the two modules successfully dock, it is not just a technical maneuver, but the moment when the hope of returning is restored. After that, the crew transfers into the main module, bringing with them everything needed for the journey back to Earth, while the section that lifted them off the Moon is left behind, drifting as a trace of the mission. And from that moment on, the spacecraft enters its most critical phase, the journey home, where no margin for error remains. But leaving the Moon does not mean they are already on their way home, because the journey back to Earth is a problem even more demanding than everything that came before. In space, there is no concept of simply turning around and flying straight back, but rather a precisely calculated falling trajectory designed to intersect with a planet that is constantly in motion. Earth does not stand still. It rotates on its axis while orbiting the Sun, and the spacecraft must aim for a target like that from hundreds of thousands of miles away with only a limited amount of fuel remaining. Even the slightest deviation in direction or timing of an engine burn can shift the return trajectory beyond any chance of correction. This is not a journey that allows trial and error, but one where every adjustment is decisive. There are moments when the engine fires for only a few seconds, yet those brief seconds determine whether the spacecraft will make it back to Earth. At such vast distances, even a small initial error will grow over time into a massive deviation. Yes, that is why the guidance system must continuously track the spacecraft's position, velocity, and direction relative to its planned trajectory. However, even when all calculations are correct, humans must still make decisions at the right moment and follow procedures with absolute precision. Because in this environment, a single moment of delay or a minor mistake can cause the entire mission to fail. Returning to Earth is, in essence, about guiding the spacecraft into the correct re-entry corridor, a very narrow region of space where it can enter the atmosphere at a safe angle. If the approach angle is too steep, the spacecraft will plunge down at extreme speed and face heat levels beyond what the heat shield can withstand. But if the angle is too shallow, then it can skip off the atmosphere and bounce back into space like an object skimming across a surface. That means survival depends on bringing the spacecraft back at an almost perfect angle within an extremely small margin of error. The challenge is that this problem is not solved at the last moment, but must be calculated far in advance, when the spacecraft is still hundreds of thousands of miles away from Earth. Many hours before reaching the atmosphere, the trajectory is already nearly locked in, and the chance of survival depends on calculations made long before that point. For that reason, the journey home is not a gentle ending, but the final test of the entire mission, where every factor, gravity, velocity, approach angle, and remaining fuel, converges within a few decisive minutes. If the spacecraft enters this corridor correctly, there is a chance of returning safely, but if it does not, the entire journey will come to an end with no second chance. And it is in this final phase that the most extreme challenge truly begins. passing through the atmosphere to return safely to Earth. After all the calculations made in space, the most dangerous part turns out to be coming back to the most familiar place. It sounds paradoxical, but the atmosphere that sustains life is also what can destroy the spacecraft within minutes. The cause is not simply friction, but the intense compression of air in front of the spacecraft as it enters at high speed, creating a layer of plasma with temperatures reaching several thousand degrees Fahrenheit, enough to melt ordinary metal. To withstand this, a spacecraft like the Apollo Command Module are equipped with special heat shields that work by charring and gradually ablating away, carrying heat away from the structure. This means that throughout re-entry, the spacecraft is protected by a layer of material that is continuously being consumed. But heat is not the only danger. The enormous speed during atmospheric entry also generates powerful deceleration forces, pressing the astronauts into their seats with intense pressure, while the cabin shakes violently and everything unfolds beyond their direct control. And in the end, everything still depends on one critical factor. The angle of atmospheric entry must fall within an extremely precise range. If it is too steep, the temperature and pressure will spike beyond what the heat shield can withstand. But if it is too shallow, the spacecraft can skip back into space, carrying the crew away from any chance of survival. In those brief minutes, they must pass through an invisible corridor where even the smallest deviation can cost lives. There is a particularly tense moment when the plasma surrounding the spacecraft blocks all radio communication, causing it to almost disappear from every tracking system on the ground. During that period, no one outside knows what is happening, and inside, the crew can only wait. As the spacecraft moves deeper into the atmosphere, its speed gradually decreases, the plasma weakens, and communication is restored. But surviving the extreme heat is still not the end. The spacecraft must deploy its parachute system at exactly the right moment to slow down before splashing into the ocean. After a journey spanning hundreds of thousands of miles and countless precise calculations, everything ultimately comes down to a few parachutes opening in the sky. And only when the spacecraft touches the water safely can the journey to the moon truly be considered complete. After everything, what makes this journey extraordinary is not just that humans set foot on the moon, but that they understood the universe well enough to make it possible. This is not a victory of sheer power, but the result of mastering the invisible laws that govern every motion in space. Gravity, the force that causes an object to fall to the ground, is also what keeps the moon orbiting Earth, and at the same time, it is the force that governs the entire path of a spacecraft, from launch to orbital flight to landing, and finally the journey back. If that means humans did not conquer space by resisting nature, but by understanding it and working with it. To travel far, they do not only need thrust, but must know when to accelerate, when to let the spacecraft drift along its trajectory, and when to make adjustments to maintain the correct path. The nature of an orbit is not to fly straight, but to exist in a form of controlled falling, where an object is constantly pulled toward a celestial body while moving fast enough to never collide with it. It is this understanding that transformed what once seemed like chaos into a journey that could be predicted and controlled, step by step, from Earth to the moon and back again. But understanding the laws of nature alone is not enough. Humans must also turn them into numbers so precise that there is almost no room for error. And from the velocity needed to leave Earth, to the timing of engine burns, the angle of orbital insertion, and even the exact moment parachutes deploy during return, everything is defined by mathematics. It may sound dry, but those very numbers are what kept the fragile lives of the astronauts intact throughout the journey. What is truly remarkable is that during the time of Apollo 11, computer systems like the Apollo Guidance Computer had far less processing power than modern personal devices. Yet the decisive factor was not how powerful the computers were, but how precisely humans understood what needed to be calculated and why. They did not rely on unimaginable technology, but on physics, engineering, discipline, and the belief that the universe could be understood through reason. And that is what makes the journey to the moon so unique. Not a miracle, but the highest limit of human understanding applied in reality. Looking back at the entire mission, every phase was filled with risk, yet all of them were tightly connected through the unchanging laws of nature. Humans did not conquer the moon by being stronger than the universe, but by understanding how it works and moving in harmony with it. And perhaps that is the greatest part of it all. A small species on a blue planet learned how to understand and read the laws that govern the sky. Because of that, they not only set foot on another world, but also returned to prove that a distance once thought unreachable could, in fact, be crossed. From that point on, the story is no longer just about spacecraft or technology, but becomes a story about humanity itself and the limits we are willing to challenge. After all the engines, trajectories, and cold precision of calculations, the journey to the moon still leads back to a deeply human question. Why would such a small species choose to leave the safety of its home to reach for something so distant? The answer does not lie entirely in science, but also in the instinct to explore, in the desire to know what exists beyond the horizon. From crossing oceans, traversing deserts, and climbing mountains, to looking up at the night sky, humans have always been driven by that same question. The moon, therefore, is not just a destination, but the greatest symbol of the curiosity that has followed us throughout history. We did not go there simply to stand on a distant surface, but to test how far our understanding could reach. And in every step of that journey, one truth remains. Humans do not accept being limited by what already exists, even when the path ahead is risky, costly, and fragile. That is what gives this journey a meaning far beyond any technical achievement. If judged purely by practical efficiency, humans might never have chosen the moon, but exploration has never been driven solely by immediate benefit. Some journeys are undertaken simply to prove that fear is not our ultimate limit. When the spacecraft leaves the launch pad, it carries not only astronauts but also the ambition and courage of an entire civilization. And when they set foot on the moon, what is proven is not just the ability to reach a distant place, but the ability to overcome the limits that once defined humanity. After that journey, the way we look at the sky changed because we realized that no distance is truly beyond reach. At the same time, humans began to see Earth differently, smaller, more beautiful, and more fragile. Perhaps that is the greatest value of this journey. It not only opened a door to the universe, but also gave us a deeper understanding of the place we call home. Because sometimes going far away is not about leaving, but about realizing why where we belong is worth cherishing. That is why the journey to the moon and back is not just a technological achievement, but a testament to humanity's drive to explore, a drive strong enough to turn cold numbers into a life-or-death journey, and to transform the silence of space into a story shared by all of humanity. And perhaps that is why this story still moves us, because it reminds us that the impossible only exists until someone makes it real. from Earth to the Moon and back again. It is not just the journey of a spacecraft, but the journey of humanity itself. After everything, the journey to the Moon and back is not just a story of technology or science, but a milestone that shows how far humanity can go when it refuses to accept its own limits. Thank you for taking the time to listen to today's story, especially for those who love documentary about space and the Moon. If you found this content valuable, feel free to share the video and leave a comment so we can continue exploring together. Don't forget to subscribe to the channel and hit like to follow the next journeys. Goodbye, and see you in the next video.